We'll start in 1 minute. Today we'll continue in section 11.2 on infinite series. So we were discussing Theorem 6. Theorem 6 says that if a series converges, then the limit of the a sub n sequence goes to 0. But the converse is not true in general. And an example to show that the converse is not true is we know that the harmonic series of the terms 1 over n as n goes from 1 to infinity, the sum of those terms diverges to infinity, even though the limit of 1 over n goes to 0 as n goes to infinity. But we can use the contrapositive of Theorem 6 for a test for divergence. So this says if the limit of a sequence a sub n does not exist, or if the limit does exist but does not equal 0, then the corresponding infinite series is divergent. So in general, when determining whether or not a series converges or diverges, it is sometimes useful to determine if the limit of the sequence is equal to 0 or not. If it's not equal to 0, then we know that the infinite series diverges. So we'll do this for this example. We'll show that the infinite series, the terms are the natural log of n squared plus 1 over 2n squared plus 1 as n goes from 1 to infinity. Show that this infinite series diverges. For this infinite series, the terms that are being added, the a sub n terms, are the natural log of n squared plus 1 over 2n squared plus 1. So take the limit as n approaches infinity of the sequence a sub n. Okay, so this is the limit as n approaches infinity of the natural log of n squared plus 1 over 2n squared plus 1. Okay, then you can take the limit directly, or you can put in one more step. The limit of the natural log of that expression as n goes to infinity. By a previous theorem that we had, we can write this as the natural log of the limit as n approaches infinity of n squared plus 1 over 2n squared plus 1. And the limit as n approaches infinity of n squared plus 1 over 2n squared plus 1 is 1/2. So we get the natural log of 1/2, but the natural log of 1/2 is not 0. So by the test for divergence, the series diverges. That's what we wanted to show. Theorem 8 gives us a list of certain things about infinite series, things that work out the way that we hope that they would. So if we have two infinite series that converge, the series of the a sub n terms and the series of the b sub n terms, both are given to be convergent, and c is a constant. Then the series of c times a sub n, as n goes from 1 to infinity, is you can factor the c out of all of the terms and then just multiply c times the series of the a sub n terms. If you have a series where the a sub n and b sub n terms are added, then you can write that as a sum of two separate series. And the same is true if you have a difference, a series involving a sub n minus b sub n as n goes from 1 to infinity. You can write that as the difference of the two series. So these seem to make sense, and as I mentioned, they work out the way we hope that they would. Okay, the next example suppose the nth partial sum of the series of the a sub n terms is s sub n equals 3 plus 5n to the second over n plus n to the second. So if the series is convergent, then find its sum. So all we have to do is try to evaluate evaluate the limit of s sub n. If this limit exists as a finite number, then that will be what the series converges to. So we just compute the limit of 3 plus 5n to the second over n plus n to the second as n goes to infinity. So we know what this limit is. I can go into more detail, but we have done some examples like this. So what is the limit, or does it exist? So maybe I should go into more detail, maybe a little bit. So we just note that this expression, 3 plus 5n to the second over n plus n to the second, it's a rational expression. Both the numerator is a polynomial in the variable n, and the denominator is a polynomial in the variable n. So one technique for trying to determine what the limit is identify the largest power in the denominator, which is n to the second, and then multiply the expression by 1 in the form 1 over n squared over 1 over n squared. So we're going to multiply the numerator by 1 over n squared, multiply the denominator by 1 over n squared. And then simplify, or do the multiplication and simplify. So 3 times 1 over n squared in the numerator is 3 over n squared. And then plus 5n squared times 1 over n squared is just 5. And also in the denominator, n times 1 over n squared simplifies to 1 over n. And n squared times 1 over n squared is 1. And now we compute the limit. 3 over n squared goes to 0 as n goes to infinity. So the numerator goes to 0 plus 5. And in the denominator, 1 over n goes to 0 as n goes to infinity. So 0 plus 1. And so the limit is equal to 5. So that means the infinite series of the a sub n terms converges to 5. So the value is just 5. Okay, in case it's necessary, the sequence S sub n of partial sums so S sub n, what's that equal to? If it's the sequence of partial sums for the series of the a sub n terms. So S sub n is the sum of the first n terms of the a sub n sequence. So S sub n is a sub 1 plus a sub 2 plus dot dot dot. The last term is a sub n. It's the sequence of partial sums. All right, let's move on to the next example. If the series is convergent, then find its sum. So the terms in the series are 3 times 5 to the negative n, and n goes from 1 to infinity. What sort of series are we looking at? It's sort of camouflage in a way, but so this is a geometric series. So we can alter the terms, 3 times 5 to the negative n. So 5 to the negative n is 1 over 5 to the n, or 1/5 to the n. Okay, so I'll remind you of the geometric sum formula. If the common ratio is between -1 and positive 1. The infinite series starting from n equals 1 to infinity of a times r to the n minus 1. That converges to a divided by 1 minus r. Okay, so in this geometric series, the common ratio is 1/5. But we need to do maybe one more thing before we can determine what its sum is. The common ratio 1/5 is between -1 and 1, so we know that it converges. Okay, but notice that in this formula, in the series, we start at n equals 1, but the exponent on the common ratio is n minus 1. We don't have that here. We have 1/5, the common ratio to the nth. But if we take one of those factors of 1/5, so 3 times a factor of 1/5, and then multiplied by 1/5 to the n minus 1, and then I'll do one more intermediate step. Three times 1/5 is 3/5, and then multiplied by 1/5 to the n minus 1. So now we have it in the form that we want. And so the sum is 3/5 in the numerator divided by 1 minus 1/5. And then it's just a little bit of arithmetic. 3/5 divided by 4/5, and that simplifies to 3/4. Okay, let's go on to the next page. Okay, this one says express the series as a telescoping sum. If it converges, then find its sum. So in this series, the terms are 2 over n plus 1 times n plus 2, and n goes from 0 to infinity. And so if you ever suspect what is referred to as a telescoping sum, then use partial fractions to rewrite the nth term of the sequence. So we'll do that here. 2 over n plus 1 times n plus 2. According to what we learned using partial fractions, this is equal to some number a over n plus 1 plus some number b over n plus 2. And we want to find the values of a and b. Okay, so if we add these two terms with different denominators, the common denominator is n plus 1 times n plus 2. So this numerator becomes a times n plus 2. We add that to b times n plus 1. And this is all divided by the common denominator n plus 1 times n plus 2. And then we determine the values of a and b. So in the numerator, we have an plus 2a plus bn plus b. This numerator, a times n plus 2a plus b times n plus b, has to equal 2. So that means, since there's no n term, that means an plus bn is 0, or the coefficient a plus b is 0. So a plus b must be 0. And the constants, 2a plus b, that has to equal the constant 2. So 2a plus b equals 2. Okay, so I guess I'll put this equation below this one. So a plus b equals 0. If we subtract the bottom equation from the top equation, we'll find the value of a. So 2a minus a is a, b minus b is 0, a plus 0, and then 2 minus 0 is 2. So a is 2, and since a plus b is 0, that means that b is negative 2. Okay, so we'll rewrite the series from n equals 0 to infinity using 2 over n plus 1 and then minus 2 over n plus 2. That is, we're using the partial fractions to write the terms of the series. And then we'll write the first few terms that we get from adding. So we'll write down what we get when we let n be 0. Then the next term that we add will be what we get when n is 1. We'll do a couple more. Okay, so the first term in the series, when n is 0, we get 2 over 1, or just 2. And then minus 2 over 0 plus 2 is 2 minus 1. Okay, the next term in the series that is added occurs when n is 1. So when n is 1, 2 over 1 plus 1 is 2 over 2, or 1. And then we subtract 2 over 1 plus 2 is 2/3. The next term that is added occurs when n is 2. When n is 2, 2 over 2 plus 1 is 2/3. And then minus 2 over 2 plus 2 is 2 over 4, or 1/2. The next term added in the series occurs when n is 3. So 2 over 3 plus 1 is 2 over 4, or 1/2. and then minus 2 over 3 plus 2, or minus 2/5. So do you see what is happening? So in this first term, the minus 1 plus 1, those add up to 0. Then the minus 2/3 plus 2/3, those add up to 0. And then the minus 1/2 plus the 1/2, those add up to 0. So it's going to do that forever. So I'll write down a few of the partial sums. So n starts at 0, so s sub 0 is the first partial sum. That's just 2 minus 1, or 1. The next partial sum is 2 minus 1 plus 1 minus 2/3. So here I'll write it as 2 minus 2/3, because the minus 1 plus 1 cancels. The next term in the sequence of partial sums is the first term plus the second term plus the third term. So we get 2 minus 1/2 for the sum of the first three terms. And another one, the next term in the sequence of partial sums. So s sub 3, since we're starting at n equals 0, s sub 3 is the sum of the first 4 terms. So here we'll write 2 minus 2/5. And so on. And s sub n is just going to be 2 minus and then 2 over n plus 2. Hey, well, the series, if it converges, is equal to the limit of the sequence of partial sums. So let's compute the limit of s sub n. If the limit exists as a finite number, then the series converges to that number. So what's the limit of this? 2. Yeah, 2 over n plus 2 goes to 0, so the limit is 2. And so we conclude that this infinite series, referred to as a telescoping sum, converges to 2. Okay, the next example, find the values of x for which the series, the terms are -4 to the n times x minus 5 to the n, as n goes from 1 to infinity. Find the values of x for which this series converges. We'll also determine what the series converges to in terms of x for those x values. So any ideas on how to go about this? Okay, a hint is, well, we have a product of two terms with, and each of those two terms is a power of n. So that reminds me of a geometric series. So this is sort of slightly camouflaged. We can write this as a single term with an exponent n using properties of exponents. So let's rewrite this. And we'll multiply -4 times the quantity x minus 5, and that will be 20 minus 4x to the n. All right, so now we can identify what the common ratio is because we have an expression raised to the power n, and n goes from 1 to infinity. So the common ratio is just 20 minus 4x. Before proceeding, though, let's get this into the form that we want. Remember the geometric series from n equals 1 to infinity. We want a times r to the n minus 1. So we have r to the n. So we'll just take one of those factors of 20 minus 4x and then multiply that by 20 minus 4x to the n minus 1. And then eventually we'll use this, the formula, the geometric series of a times r to the n minus 1 as n goes from 1 to infinity is a over 1 minus r. So first, the common ratio has to be between -1 and +1 if it's going to converge. So 20 minus 4x, let's write -1 is less than 20 minus 4x, which is less than +1. And then we just solve this compound inequality. First, I'll subtract 20 from all three parts. So we get -1 minus 20 is -21 is less than 20 minus 4x minus 20 is -4x in the middle. And that's less than 1 minus 20 or -19. We want to solve this compound inequality for x. So what do we do next? Divide each of the three parts by -4, and since we're dividing by a negative number, we have to switch each of the two inequalities to the opposites. So we're going to divide each of the three parts by -4. So -21 divided by -4 is +21/4. And since we're dividing all three parts by a negative, we switch this from less than to greater than. And then in the middle, negative 4x divided by negative 4 is x. Switch this from less than to greater than. And then negative 19 divided by negative 4 is 19/4. This is an okay compound inequality, but you might prefer the smaller number to be on the left instead of on the right. So we could just rewrite this as 19/4. This means 19/4 is less than x, so 19/4 is less than x, while x is less than 21/4. Okay, so the series converges for these x values. And what does the series converge to? I'll just rewrite it this way. What does the series converge to for those x values? Okay, our intermediate work up here, and this formula. So 20 minus 4x goes in the numerator. And in the denominator, we have 1 minus the common ratio, which is 20 minus 4x. So 1 minus the quantity 20 minus 4x. So 20 minus 4x over 4x minus 19. Okay, let's look at the miscellaneous problems. The first one, find the area inside the polar curve, r equals 3 times cosine of theta, and outside the polar curve, r equals 1 plus cosine of theta. So it might help to graph both of those on the same grid. We'll graph the r equals 3 times cosine of theta in rectangular coordinates, and then graph the polar curve using the rectangular coordinates. Okay, so r equals 3 times cosine of theta in rectangular coordinates looks sort of like this. And then r equals 1 plus cosine of theta, first in rectangular coordinates. So this will be like that, roughly. Okay, so the polar coordinates, first r equals 3 times cosine of theta. So when theta is 0, r is 3. Then between 0 and pi over 2, the r values are positive, but they go to 0. So we're just going to get a circle for this one. And then from pi over 2 to pi, the r values are negative. So the graph and the polar curve will be in the diagonal quadrant. So down here. And then from pi to 2 pi, it just retraces the same circle. Okay, to graph the other polar curve, we start out with r equals 2. When theta is pi over 2, the r value is 1. So it's going to do, this is one of those cardioids that looks something like that. Between pi over 2 and pi, the r values are short, and then they get to 0. And then between pi and pi over 2, they go back to 1. And then there's a intersection. It's a horrible graph, but okay, so we want to find the area that's inside the polar curve r equals 3 times cosine of theta, but outside of the polar curve r equals 1 plus cosine of theta. And we can see that this is a relatively accurate graph. The polar curves intersect here and here. So how do we determine what the theta values are where they intersect? The same thing that we would do if we wanted to find where two polynomials intersect. We set the functions equal to each other. Okay. So we set 3 times cosine of theta equal to 1 plus cosine of theta. We'll subtract cosine of theta from both sides, so we get 2 times cosine of theta equals 1. Divide both sides by 2, cosine of theta equals 1/2. Well, we know that cosine of theta equals 1/2 if theta is equal to pi thirds. And rather than going full circle, so to speak, let's just use theta equals negative pi over thirds. Okay, so on the interval from theta equals negative pi over 3 to theta equals pi over 3, we're just going to subtract the area of the inner curve from the outer curve. So the area that we want is the integral from negative pi over 3 to pi over 3. And remember what the integrand is when you're trying to find the area enclosed by a polar curve. is 1/2 r squared. Okay, so the first one, 1/2 times 3 cosine of theta all squared, 3 times cosine of theta squared. And then from that, we are going to subtract 1/2 times the other r value squared. Okay, so I'll just take this a couple of steps further. You've seen integrals like this before, but we'll do a little bit more arithmetic. When we square 3 times cosine of theta, we get 9 cosine of theta squared, so we'll multiply that by 1/2. So we get 9/2 times cosine of theta squared. And then we're going to subtract 1/2 times the quantity 1 plus cosine of theta squared, which is 1 plus 2 times cosine of theta plus cosine of theta squared. And I think I'll leave the rest of this for you to do. Simplify the integrand a little bit more and combine the cosine of theta squared terms. And then when integrating, use the identity for cosine of theta squared. So cosine of theta squared, when integrating this formula, 1/2 plus 1/2 times cosine of 2 theta, seems to be a pretty handy formula to use when integrating. Okay, let's look at the next one. Find the limit of the sequence. A sub n equals 1 plus k over n raised all the quantity raised to the power n, where k is a constant. So did anyone work on this and find the answer? Okay. So the way I did it was I'm going to take the natural log of a sub n, write it as, so the natural log of 1 plus k over n to the n. And using properties of logarithms, the natural log of the quantity 1 plus k over n to the n, the exponent n can be written out front. So it's n times the natural log of 1 plus k over n. And then I'm going to rewrite this as the natural log of 1 plus k over n over 1 over n, because 1 divided by 1 over n is the same as n. And now we'll work on the limit. The limit as n approaches infinity of the natural log of a sub n. Well, that's just going to be the natural log of the limit as n approaches infinity of a sub n. And so we'll compute the limit as n approaches infinity of the natural log of 1 plus k over n over 1 over n. So what does if we just computed the limit of this, what would we get? If we let n go to infinity, then what does the natural log of 1 plus k over n get close to, and what does 1 over n get close to? Is 0 divided by 0? Is that what you said? Yeah. K over n goes to 0, but the natural log of 1 is 0, and 1 over n goes to 0. So we use L'Hopital's rule. Compute the derivative of the natural log of 1 plus k over n with respect to n, and then take the derivative of 1 over n with respect to n. Okay, so when we take the derivative of 1 plus k over n, we get negative k over n squared, and then this is divided by 1 plus k over n. And then the derivative of 1 over n with respect to n is negative 1 over n squared. Okay, we're out of time. I guess the rest of this, just do the arithmetic, and that's all we have time for today. So go ahead and sign in for attendance.